Hi, welcome to another lecture in the Organic Chemistry Lab series. In this video, we will talk about the synthesis of cyclohexene starting from cyclohexanol. This is a dehydration reaction, which is one of the elimination reactions that can be used to prepare alkenes from alcohols. So cyclohexene can be prepared from cyclohexanol via the dehydration reaction. This is an acid catalyzed reaction and it is a reversible reaction, as we will see in a moment. So in this reaction, cyclohexanol, which is an alcohol, will lose a water molecule. So it will lose an OH from one carbon and a hydrogen from another carbon. And this will lead to the formation of cyclohexene, which is an alkene, and water. This is an acid catalyzed reaction. H2SO4, concentrated H2SO4 or concentrated H3PO4 can be used as acid catalyst in this reaction. Now, in the previous example, which is a dehydration of cyclohexanol, if we remove the hydrogen from this carbon or from this carbon, which are called the beta carbons, we are going to get the same product. So whether we are going to get this cyclohexene or this cyclohexene, this is the same thing. However, in certain cases, we may have more than one option. And in order to know which product is the major one, we have to follow Zaidzev's rule, which states that the major product can be obtained by removing a hydrogen from the carbon with less hydrogens. Let's take an example to understand this. For example, in this case here, which is a methyl cyclohexanol, this is the carbon which is bonded to the OH, and this is usually called the alpha carbon. Now we have two beta carbons. We can either remove a hydrogen from this beta carbon, or we can remove a hydrogen from this beta carbon, and each one is going to give us a different product. So the first product could be this one, which is by removing this OH and this hydrogen which is here. And the second product, which is this one, could be obtained by removing again this OH and the hydrogen from this carbon. So we are going to get two different alkenes. Which one is the major one? This is the major one. Why? Because according to Zaidzev rule, the major product is obtained by removing a hydrogen from the carbon with less hydrogens. Now, if we look back at these two carbons, we can see that at this carbon here, we have only one hydrogen, whereas at this carbon here, we have two hydrogens. So according to Zaidzev rule, removing from this side will give us the major product, and that's why this is going to be our major product. Let's take another example just to make sure that we understood this idea. For example, if I started with this compound where an OH is here, again, upon dehydration reaction, H plus and heat, first of all, I have to draw the products. This is my alpha carbon, and these are my beta carbons. So we can get two different alkenes. The first one is this one, and the second one is this one. So those are the two possible alkenes. Which one is the major one? At this carbon here, we have three hydrogens. At this carbon here, we have two hydrogens. According to Zaidzev rule, we can get the major product by removing from the carbon with less hydrogens. So this is going to give us the major product. And that's why in this case, this is going to be the major product. So this is how we draw the structure of dehydration products starting from alcohols. And this is how we identify the major product using Zaidzev's rule. Now let's talk more about the reaction, the dehydration reaction itself. Well, this is a reversible reaction. So because alcohols in the presence of acid and heat are known to give alkenes and water, and the same thing happens in the opposite direction. So if I have an alkene and we add water to it in the presence of an acid, we can get back the alcohol. So both reactions are actually known in organic chemistry. Dehydrations of alcohols to alkenes and hydration of alkenes to alcohols. That's why this is a reversible reaction, so it can go in both ways. In order to push this reaction to go to the right, so to push the equilibrium to go to the right, the reaction is usually done in a distillation apparatus. And the reason for doing this is that cyclohexanol has a higher boiling point than alkene. So if the reaction is taking place, let's say in this reaction flask, and we are heating here, once cyclohexene is formed, it will go up and pass through the distillation setup, and then it can be collected on this side. Now, same thing happens for water. So basically, once water and cyclohexene are formed in the reaction flask, by the action of heat, they will evaporate and go through the condenser into the other side. Now, what we are actually doing is that we are removing the products from the equilibrium. And according to Le Chatelier principle, when we remove the products, the reaction will go to the right. So it will shift to the product side. And this is how we can increase or maximize the yield of the reaction. So again, we are using a distillation apparatus in order to be able to separate cyclohexene and H2O, which are the products. And in this way, according to Le Chatelier principle, we are pushing the equilibrium to the right, and we are maximizing the amount of the products that we get. And this is the main reason for using the distillation setup. The alkene has a lower boiling point than the alcohol, and that's why it will easily evaporate, whereas the cyclohexanol will stay in the main flask. In the receiving flask, which will contain the cyclohexene and water, this is going to be a heterogeneous mixture, because cyclohexene, which is the organic product, is insoluble in water, and that's why we may see two layers here. The first one, the top one, is for cyclohexene, which has lower density, and the second one is for water. So usually water will be at the bottom and cyclohexene will be here because it has a lower density. Also, there's one more thing which should be taken into consideration, is that the receiving flask should be placed in an ice bath. And the reason for doing this is that cyclohexene has a low boiling point. So if we didn't do this, we may lose our cyclohexene by evaporation. So we want to decrease the temperature as much as possible so that the collected cyclohexene doesn't evaporate, and in this case the yield or the collected amount of cyclohexene will be very low. In fact, you will be able to know that cyclohexene easily evaporates by due to the smell of cyclohexene, which you are going to smell in the lab. So this is a reason for using an ice bath in the reaction. And the last point is that usually, in order to, if like let's say this reaction flask has H2SO4, let's say some H2SO4 droplets were able to go into the other side, we can neutralize the solution by adding sodium bicarbonate, NaHCO3. And if NaCH3 reacts with acid, we are going to see or notice that CO2 gas is being produced. Now, how can we make sure that the collected product in the receiving flask is actually cyclohexene and not something else? Well, cyclohexene is an alkene, and alkenes usually can be detected by one of the unsaturation tests. So whenever you want to check if an alkene or a double bond is present, we can either do the bromine test or the permanganate test. What is the bromine test? Usually bromine is a red colored solution. So if we want to know whether a double bond exists or not, we just add few droplets of bromine to the solution which is being tested. If the red color of bromine disappears, this indicates that actually a double bond exists. Whereas if the red color persists, this means that there is no double bond. The same thing happens in the permanganate test. And again, in the permanganate test, which the potassium permanganate has a purple color. Once I add few droplets of permanganate to the solution and they disappear, I can know that this solution contains a compound which has a double bond or a triple bond. In this case, it's going to be a double bond. So usually the bromine test or permanganate test are used to test for unsaturation or to test for the presence of double bonds. And this applies in this case here for the cyclohexene. So if you want to know whether cyclohexene is formed or not, we can do the bromine test and the permanganate test. If they both give colorless solutions, this means that yes, cyclohexene is formed, whereas if the red color of bromine or the purple color of permanganate didn't disappear, this means that the reaction didn't work. Now let's talk about the dehydration mechanism. So cyclohexanol can be converted into cyclohexene via an elimination reaction mechanism. The first step in this mechanism is usually the protonation step. The OH group is a bad leaving group. So in order to help this OH or to kick out this OH group, we have to protonate it first, so it attacks H+. Of course, this is a reversible mechanism. So the first step is protonation, and protonation converts OH into OH2+, which is a good leaving group. Now the OH2+ leaves, and this leads to the formation of a carbocation. And the last step is the removal of a beta hydrogen, so either HSO4-, which is formed, attacks here, and this goes here, and this is how you make the double bond. So this is the elimination or dehydration mechanism. Now, if the alcohol is primary, usually the mechanism will be an E2 mechanism instead of this mechanism, which is an E1 mechanism. So this is called an E1 mechanism because it involves the formation of a carbocation after the departure of the OH group. So this is the dehydration mechanism of cyclohexanol into cyclohexene. This was a mistake.